My name is Josh Gordon, and I work on the TensorFlow team. And this talk, as you can probably see, is an intro to deep learning. It's a little bit long, but we'll get through as much as we can. And if you like this content, we should have a long version of this talk on our YouTube channel in about a month. But anyway, what we'll cover is just some demos to get started. And then we'll take a look at what deep learning actually is. And we'll take a look at a few different families of neural networks, and then we'll take a look at a cartoon diagram of a deep neural network and begin dissecting it a little bit. And I hope you can see my screen when it's not maximized. I need to be able to see folks on chat, so hopefully this will work for you. And then we'll look at some educational resources if you like this stuff. So for starters, to take a look at a couple demos, and you may have seen these before, and you can find a link to them on the TensorFlow blog at the bottom of the screen, or if you don't want to type that in, you can search for TensorFlow blog face and hand tracking. The point that I want to make is there's a lot of existing models that are ready to go off the shelf. And without even writing any code, one way to get started with deep learning is to download an existing model. And you can see two here. One is for face tracking, and it's identifying different key points on someone's face, and the other is for hand tracking. And what's nice is these are both written in JavaScript. So deep learning is not only for Python anymore, but it's also for JavaScript developers. And what's really cool is they can run in the browser. And just looking at these, there's a lot of low-hanging fruit in deep learning because this technology is so new. And if you have a model that can identify like key points on someone's face, right off the shelf, you can imagine there's lots of applications you could build. Maybe if maybe she's movement impaired, and she could control a mouse cursor using her head. So there's a lot of things you can do without even writing any code. If you haven't seen it before, there's another interactive demo that I wanted to refer you to called the Teachable Machine. And if you're ever teaching a machine learning course yourself, this is a really excellent resource you can use to get started. And it's a way to train a computer vision model live in the browser, also without writing any code. And this can be really valuable to show students or folks in your developer group, exactly like what computer vision can do. And it's also a great way to explore, what works and what doesn't work. For instance, if you train a computer vision model to recognize whether you're smiling or frowning, you can explore what would happen if you have, emotions the model hasn't seen before. Anyway, there's a lot of value in JavaScript side of machine learning these days, and I'd encourage you to check it out. With all that said, let's take a look at what deep learning actually is, because there's a lot of terminology floating around in the field these days. I just wanted to break it down a little bit. So basically, there are three different circles here that I've borrowed this diagram. Sure, I'll present. I won't be able to see questions anymore though, but it is what it is. So there are three different circles on this diagram. And the outermost circle is AI, and then one in from that is machine learning. And then the two inner circles are very closely related. They're representation learning and deep learning. And just to knock out some definitions very quickly, when you say you're doing AI, what that really means is, you can think of a problem that people are very good at, but computers are very bad at. And the classic example of that could be programming a computer to play chess. And when you're doing AI, you can solve that problem in any way you like. So for example, you could write a rule-based reasoning system to play chess by doing something like minimax and searching the game space. Machine learning is a fancy word for programming with data. And this has been around for many, many, many years. And what's kind of funny is things that you would learn about in an intro statistics class are now called machine learning. So a classic example of that would be something like linear regression. And what machine learning really means is finding useful values for parameters. And that's a fancy way of saying if you have a model like y equals mx plus b to find the best fit line, your two parameters are m for the slope and b for the intercept. And basically, you'd start with a small random value and you'd adjust it over time to fit the line. Other really important techniques are things like decision trees or logistic regression. Anyway, then you go into a field called representation learning, of which deep learning is a subset. And that addresses a key limitation of classical machine learning techniques. And that's basically the need for having features. And here's the basic idea of what it means to need to have features. Let's say you're in classical ML, your workflow is on the left. And the most important parts of this are, thinking about the problem that you want to solve and collecting training data. But then before you train a model, you need a way to extract features from your training data. And typically, when you're doing things like decision trees or logistic regression, usually you have something called structured data. And that's a data set that you can fit, that's tabular data that you can fit in a database or inside a CSV file. And typically with tabular data, you have a small number of features that you and I as people can reason about. So maybe in a medical setting, perhaps you have a CSV file that predicts somebody's risk of heart disease. And maybe you have the patient's height and weight and blood pressure and some other data about the medications they're on. But typically you have a small amount of features that you can feed into a model like a decision tree. And this is incredibly valuable because if you train a model like a tree on structured data, you can print out the tree and you can see exactly how the model works. The challenge with classical ML is that it's very hard to work with high dimensional data. So instead of tabular data, which is structured, imagine you have unstructured data. And that could be something like a picture if you're doing computer vision, or it could be something like text if you're doing natural language processing, or a wave file if you're doing audio. And the challenge with unstructured data is that you don't have features that are readily available to reason about. So if I give you an image and ask you to tell me if it's a cat or a dog, the challenge is that the features you have to work with are just the pixel values from the image. And if you think about, if you have some experience with machine learning, try and in your head visualize what a decision tree would look like if you trained it on unstructured data, say the pixels from an image. The root node of the tree would have to say something silly like, is pixel value 70 greater in intensity than 128? And that's not a sensible way to reason about images. So classical ML fails. What deep learning basically does is it automatically finds useful features from the data. And I'll show you what that looks like. And it means that you can apply machine learning models to unstructured data like images and text and sound. And it's incredibly effective. And here's a cartoon diagram of neural network that we'll pick apart a little bit later in the talk. But roughly, what we're looking at here is a series of dense layers, which are the most common type of layers in deep learning. And at the very top of the image, we're looking at a vector. And the different colors represent different values in the vector. And you can imagine that maybe the input vector to this network are pixels from an image. The way to look at this diagram is the very last layer in this network is the one that classifies the data. And each of the green circles corresponds to an output class. And they're all going to have numbers on them when we feed this image through the network. And we'll classify it by selecting the output circle with the highest value. If you've taken a machine learning class, the output layer you can think of as doing softmax regression or multi-class logistic regression. And you can think of the intermediate layers as doing automatic feature extraction. And here's the cartoon idea of how this works. So initially, you feed pixels into this network. The circles or neurons or units in the first layer automatically learn a combination of their inputs and their weights. And you can think of them as each of the outputs from this layer are simple features. So basically, combinations of pixel values might give you simple lines or simple edges. And the width of the layer indicates basically how many different types of features of that type you can learn to detect. So this layer might be detecting like 15 different types of edges. The next layer, instead of receiving the pixels as input, is receiving the features learned by the layer above it as input. So the next layer is receiving combinations of edges. And if you think about combinations of edges, that enables the layer to learn basically simple shapes. And then the last layer is classifying the image in terms of the shapes. And it's much, much easier to classify an image in terms of the shapes than in terms of the raw pixel values. And the deep in deep learning refers to the fact that a lot of problems, especially in computer vision, at least those are the easiest for us to visualize, have this hierarchical structure where the deeper your network is, meaning the more layers you have, the more types of features it can learn to recognize. And typically you'll go from pixels to edges to shapes to textures. And if you have something like a 20-layer network, you might even have a layer in there that begins to recognize high-level concepts, like maybe whether there's an eye within the image. And the deep learning basically refers to automatic feature engineering or representation learning, which is a fancy way of saying it's learning a representation of the data that makes it much easier for the network to classify. And this is unbelievably powerful. There's one of the most interesting results in computer science in the last, I think, 5 years or so, and something you can check out yourself if you try a code example called Deep Dream. It's a technique to investigate the type of representations learned by a network. It's one thing to train a neural network to classify cats and dogs, but it's a much more interesting problem, and that's very important, but it's a much more interesting problem to ask the question of how is it that the neural network is so effective at classifying data? And there's techniques like Deep Dream that are one way to poke around with what's happening inside the network. And here you're looking at visualizations of the features that different neurons in different layers have learned to detect. And so on the left, we're looking at an early layer in the network, and each square represents a pattern that would excite one of the neurons in that layer. And you can see that there's different types of edges. And as you move to the right on the image, we're going deeper in the network. And here we found different textures and patterns, and eventually parts of objects that all excite different neurons. And some of these are a little bit trippy, and some are very beautiful. Like you can see in the top right here, here's a gorgeous picture of flowers. The reason that a lot of these are semantic is all of these depend on the data set that's used to train the neural network. And the reason different neurons have learned to recognize flowers and parts of buildings, and it looks like folks playing soccer, is because the data set contained those images. And this is an artifact of training a classifier for something like computer vision. And I'm going to skip some slides just to keep this talk moving faster. Anyway, one thing that's very nice about deep learning today, because we're a solid 6 years now into, well, more than that, more like 8 years into open source deep learning frameworks, is that it's become very easy to define different types of neural networks in code. And we kind of have this funny situation where it's very quick to write the code for the neural network, but it takes a much longer time to understand in detail what's actually happening inside that code. And my advice to you, if you're new to this, you can visit TensorFlow.org, which is an open source deep learning library. And there's 25 different tutorials that can help you get started with lots of cool topics. Play with them and play around with the code. And after you find something that interests you, then take your time to dive back in and see how it works. And all of this stuff takes about a year to learn. But roughly, I just wanted to show you some code at a high level for how easily you can define different types of models. So here's the simplest model I could think of. And this is a model for logistic regression. I'm sorry, for linear regression. And the way to read it, we have a dense layer with a single neuron and no activation. And what that says is this model can produce a single output value between positive and negative infinity. So you can train this to do linear regression. If you'd like to train a model to do logistic regression, you can add an activation function or a squashing function to that output. Now you have a model that produces one output value that ranges between 0 and 1. So this is how you define a model for logistic regression. It's code light, but concept heavy. It takes a little while to learn what a sigmoid is, but writing the actual code is quite easy. If you'd like a neural network, if you'd like a model that produces 10 output values, you can change 1 to a 10. And now you have a layer with 10 output neurons. And in this case, it has an activation function called softmax. And the way to read this is this model produces 10 output values, each of which ranges between 0 and 1, and they all sum to 1. So this is a probability-like distribution, and it's something you would use if you were doing classification or multi-class classification. If you'd like to define a neural network, you add a second dense layer. And the way to read this, when you have a design for a network like this, you always read it, the best place to understand how it works is looking at the output layer. So regardless of the intermediate layers, this model is still producing 10 outputs, all of which, 10 outputs in a probability-like distribution. But if you look at the first layer now, we have a dense layer with 128 units or neurons. And what that dense layer is doing is it's doing feature extraction. So it will take some input data and it will produce a vector of 128 outputs, which is processed by the next layer in the network to produce 10 outputs to actually classify the data. And unlike techniques like decision trees, it's usually a mistake to reason too closely about what's happening inside that dense layer. And if you're familiar with gradient descent, the way that all of these models are trained is using gradient descent. Basically, all of the weights inside the model are initialized to small random values, and they're adjusted over time. The way we get the gradients is using an algorithm called backpropagation. And basically, when we're training a model like this, we're doing gradient descent in very high dimensional space. And it's a little tricky to reason about exactly what's happening there. Anyway, as if we have time, we'll see later in the talk, all of the intermediate layers inside the network need something called a nonlinear activation function, which sounds fancy, but as you'll see, the math for actually classifying an image with this network isn't nearly as fancy as it looks. It's basically a series of matrix multiplies. And there's kind of a funny point I'd like to make. In one sense, deep learning is sequential matrix multiplication. And the point that I want to make is the value of marketing. If deep learning had been branded as sequential matrix multiplication, it would probably have seen a lot less uptake than if it was branded as deep learning. Anyway, we'll look at this later. You need the activation function to prevent those from collapsing to a single matrix multiplier. And then you can define a deeper neural network by adding another dense layer. So again, it's code-like, but concept-heavy. One really important part I'd like to make is a lot of this talk is it's quick talk, but this talk is really about what's happening inside these neural networks and what's a neuron and what's a dense layer. And that's all well and good, but the truth is when you're doing deep learning in industry, actually defining the neural network is by far the smallest part of your job. And these tasks are where you actually spend your time. And this is true regardless of whether you're doing classical ML or deep learning. The most important skills that you can learn in deep learning are really thinking through the problem end to end. What that really means is, what are you trying to classify or predict? How will it help users? How will they interact with your software? How can you be sure that your software is reliable and works well in practice? How can you have confidence that your model is doing the thing that you think it's doing? And basically skills like evaluation and testing, while they might sound less boring than they might sound more boring than the code it takes to define the deep neural network, are actually really where the value is. And I wanted to just to drive that point home. The best example I can think of is this screenshot here, and this is a screenshot of the homepage of the Journal of the American Medical Association. And this is about 6 months out of date. But what I wanted to show you on the top right corner of the screen is if you look at the most cited paper in this medical journal in the last 3 years, this was a piece of work applying computer vision by Lily Peng and others to basically help predict whether or not a patient has a condition called diabetic retinopathy. And the key point, I mean, this is a big deal being the most cited paper. She did amazing work. And the key point that I want to make is the contributions of this paper were in thoughtfully applying an existing computer vision model to the medical domain in a really precise and careful way, with solid evaluation and good testing. It wasn't a computer vision paper, it was an application paper. And all of the skills to make this possible were in the buckets that are highlighted here. The model they used was off the shelf. And you can have an enormous amount of impact without necessarily reinventing the wheel for computer vision models. It's basically finding an important problem and solving it end to end is really the most important skill if you're doing applied work. Anyway, there are many different families of neural networks, and I just wanted to give you a quick overview and point you to some tutorials. And if any of these interest you, you can click on the links below, or you can pause the video and Google for them and try them out. Basically, just give me 1 sec to clear my voice. The most common and generic type of layer in deep learning is something called a dense layer, and that's what you briefly saw in the cartoon diagram. And dense layers take vectors as input. In deep learning, everything is a vector. And if you have a data like an image, you can convert that to a vector, or you can vectorize text as well, or whatever you want. Anyway, we have a good example of how a deep neural network built only of dense layers can be used for regression. And here we have a structured data set, and this is a simple thing where you want to predict how many miles per gallon a car gets based on features like the number of cylinders and the horsepower and so on and so forth. And this tutorial will show you how to do that. This is an example of using deep learning for structured data, and you can definitely do that. But the truth is, unless you have an enormous amount of structured data, like probably hundreds of thousands or more rows, classical techniques like random forest and gradient boosted trees usually will outperform it. But you can still do it. The real advantage of using deep learning with structured data is when you work with multimodal data. So for example, if you had an image and some structured data about that image, you could feed both of those at the same time into a neural network, and you could learn jointly from that data. Anyway, there's another type of model called convolutional neural networks. And these are designed for things like image classification. And basically, a convolutional neural network is something that takes maybe an image as input, and again, it produces a prediction as output. So you can use these again for classification or regression. A really cool thing about convolutional neural networks, we've got a great tutorial you can check out for image classification, but we have another really good one for sound classification. And one way that I like to classify sound is by converting the wave into an image. So you can imagine that what sound is it's a time series. But one way to convert it into an image is you can do something like an FFT, and you can get a spectrogram, which is basically a picture of the audio file. And so if you have a convolutional neural network that can classify images, you can use the same technology to classify pictures of sound. And you can use this to train an audio recognition model that can detect things like yes, down, left, right, things like that. Or like yes, no, up, down, left, right, stuff like that. Sorry, late night, hence coffee. Anyway, another really powerful thing you can do with convolutional neural networks is something called transfer learning. And this ties back into representation learning. So basically, when you're training a neural network to classify images, two things are happening. One, you have the predictions from the very last layer in the network. If you think back to our cartoon diagram that actually classifies the data, you also have the fact that the intermediate layers are being trained to recognize different features. And the idea in transfer learning is that you can reuse the intermediate layers that recognize features that have been previously trained on one task, and you can apply them to a new task. And this is very helpful because the most important thing when you're training a model is the size and the quality of your data set. And we almost never have as much data as we would like. But in transfer learning, if you reuse these features that may have been previously trained on a very large data set, they can help you learn a model with a smaller amount of data because you don't need to learn the image processing from scratch. And you can try that out at the link below. There's another family of neural networks called recurrent neural networks. And these are a way of working with sequence data. And I have, I think, 2 or 3 examples of sequence data on these slides. The first one is text. And you can think of text, of course, as a sequence of words or a sequence of characters. And there's 2 things you can do with text. One is boring and one is cool. Boring and useful, and one is cool but maybe less useful at the moment. The boring but useful thing is basically doing text classification. And the classic example of this is something like sentiment analysis. And we've got a great example where you can find, this is from the IMDb data set. It's a collection of movie reviews, and you can classify every review as positive or negative. And on the right, we have a fun example of how you can generate text. And here we have an end-to-end example that will help you download a giant text file that has a collection of all of Shakespeare's writing. And the model will learn to generate new text in a Shakespearean-like format. And if you read it, it looks like Shakespeare, but it's of course meaningless, but it is still pretty cool. Another really wonderful interactive demo you can try, it's called SketchRNN. And the basic idea here is this is a demo that will help you draw with a computer. And the idea is you start drawing a shape, and SketchRNN will attempt to auto-complete your shape. The way this works is if you think about what a drawing is, a drawing, it's not just the completed picture, but a drawing is a sequence of brushstrokes. And the idea with SketchRNN is this was trained on a very large database of people drawing these little line images of like airplanes and bicycles and trees. And the sequence data of these drawings was saved and was used to train an RNN to help you auto-complete drawings. And it's interactive. You can try it in a browser. It's great with kids, and they really enjoy it. And it's also a really great way to think about novel applications of sequences. So what can you do with sequences that aren't just text? And then if you're working with time series data, we have, you can also use RNNs for that. We have a really great tutorial that shows you how to basically forecast the weather. And so we have a data set that contains weather information for like the last few years, and that might have features like temperature and pressure and humidity. And you can use that to train a climate model to predict the weather next week. That tutorial is actually more of like a book chapter. A friend of mine wrote it, Mark. He did an amazing job. There's a lot of really good information in there. You can check it out. There's another really powerful family of neural networks called encoder decoders. And this is extremely important. You can use them for sort of all the fun and semi-mystical applications of deep learning that I would have thought were impractical less than 10 years ago. The basic idea is that an encoder takes some data and learns a representation for it and compresses it into a vector. So an example could be, you could feed a sentence. So here you have a sentence in English, can I borrow this book? And the encoder, in this case, it could be an RNN, will learn a vector representation for the sentence, which is kind of crazy if you think about it. A vector is a sequence of numbers, and the size that you might learn here might be 128. So the task that you're trying to do is compress the information in a sentence into a vector, which is extraordinary that it works. Then you have a second neural network called a decoder, which decompresses from this vector into a sentence in Spanish. And what you're looking at here is this is a model for machine translation. And what's really extraordinary about this is the only thing you need to train this model is a parallel corpus. So that's the sentence in the source language followed by the translation into the target language. And if instead you would like to train a model for Spanish to English, the only thing you need to do is swap the order of the source and the target language in your training set. It's incredibly valuable, and all this is without doing any kind of statistical machine translation. You don't need fancy parsers, you don't need any features at all. It's all learned end-to-end. A very similar technology with encoder decoders is you can go from an image to a sentence. And this is an example of image captioning. Again, you can find a complete end-to-end tutorial at the link below. And here we're taking an image as input, and the encoder is learning a vector representation for the image. And the decoder is producing a sentence to describe the vector. So here the input is a picture of a surfer riding a wave, and the output of the network is a sentence that captions the image. So it says something like, here it says, I see a wave and a surfer, something like that. It's unbelievably cool. A much simpler example of an encoder decoder, and again, you can find a complete tutorial at the link below, is something called anomaly detection. And here we're doing this using an autoencoder. An autoencoder is a special type of neural network that learns to reproduce its own input. And the basic idea here is we have a data set, and you can imagine it has many electrocardiograms. And they're all in a simplified format. So it's basically a time series that describes the electrical activity maybe in your heart. And the idea is if you have a data set like that, where almost all of the examples are normal and a small number of the examples are abnormal, what you can do is you can train an autoencoder that tries to reproduce its own input. And the intuition is that it will struggle to reproduce the abnormal examples because there are very few of them. And then you can look at the reconstruction error. I know I'm flying through this, and it's always challenging giving talks when I can't see anyone in the audience. This is just a quick overview. And if you're interested in any of these topics, the thing to do is check them out at the link below. And there's educational resources that you can use to dive deeper. There's one more family of neural networks that I'll talk about briefly, and then I think we'll take a look at what's actually happening in these things under the hood. This is a family of neural networks called GANs, or generative adversarial neural networks. And all of the examples we've looked at so far, or almost all of them, are doing things like classification or regression. You're predicting an output. And that's true even when you're doing image captioning. You're predicting the next word in the sequence. A much harder problem is building a generative model. And the idea here, and again, is we have a model that is trying to produce an image, basically, that looks real. And it's a much harder class of problems. Here, there's a very beautiful model out of Berkeley called Pix2Pix, and it's a type of model that happens to be called a conditional GAN. But basically, on the left side of your screen, it's taking an input image, which is a block diagram of a hotel. and it's trying to synthesize a photograph that matches to the input image. And it works surprisingly well. Again, even though these models are all doing these different extraordinary things, they're all trained end-to-end in exactly the same way, using gradient descent to optimize the weights and backprop to get the gradients. And it's this very general class of techniques that's applicable to all these different problems. One last area of deep learning that I think is increasingly important is graph neural networks. And in the same way, so a neural networks are representation learning. A CNN learns a representation for an image, an RNN learns representation for a text, and a GNN, or a graph neural network, learns a representation for an image. There's a really outstanding paper that I'd recommend you check out. It's called Deep Learning Approach to Antibiotic Discovery. And the basic idea here was to predict whether a drug had antibiotic properties. And what's great about this is you can represent a drug as a molecular graph, and you can feed that graph into a GNN. And the GNN will learn a vector representation for the molecule. And then you can classify it as being an antibiotic or not an antibiotic. So this enables us to apply deep learning to a new class of problems called graphs. Obviously, graphs are incredibly general. You can think of things like representing roadways and traffic as a graph, or much more important things like molecules. I think we saw earlier a really great example of a healthcare paper for diabetic retinopathy prediction. But what's really important about GNNs is they take deep learning, I think, into medicine and drug discovery. And so I suspect, and I'm really crossing my fingers, that in the next few years, we're going to see more papers like this that have real world impact. Anyway, there's a misconception that neural networks are opaque. And they're definitely much more complicated to interpret than things like a decision tree. But there's probably two classes of techniques that I wanted to draw your attention to help you understand what's happening inside a neural network. One such technique that we've briefly talked about is deep dream. And this is on the investigation side, where how do you understand what these different neurons are doing? And in a nutshell, you can find tutorials below, but what deep dream can do is it can find an image that helps you to explain what's happening inside a single neuron in the network. There's a second technique called integrated gradients. Neural network classified a particular image the way that it does. And rather than explaining the whole model, so if you have a decision tree, you can explain the entire model just by printing it out. Integrated gradients for neural networks helps you explain only one prediction at a time. So it's much more limited. But the idea here on the top right corner of the screen, I know it's small, but there's a picture of a fireboat in the San Francisco Bay. And it's a fireboat because it's spraying water. And on the lower right corner of the screen, we've asked the model to explain why it thought this image was a fireboat, as opposed to maybe any other class or a different type of boat. And if you see the purple, what the model has done is it's highlighted the water spouts. And it tells us that that is the chunk of the image that was important to its decision. So you can use this to explain, one technique at a time. And now continuing this warp speed talk, let's take a quick look at what's actually happening inside a neural network and pick apart this cartoon diagram a little bit. And here I just wanted to take a look at the forward pass. And by the forward pass, I mean, what happens when we actually classify some data with the network so we can see what all these different pieces actually are. We're not going to talk about optimization right now for time. So the best place to start is let's take a look at exactly what one of these little neurons is. And a neuron here is a little circle. And there's a couple different ways of explaining this. On the left, there's a graphical diagram. And if you prefer math, on the right, there's math that shows exactly the same thing. On the far left, we see x0, x1, and x2. And these are the inputs to a neuron. And these can be pixel values from an image, or they can be elements of a vector. Basically, they're real numbers that we're feeding into the neuron. And then the lines represent weights on the left. And we have theta 0, theta 1, theta 2. And what the thetas are, these start life as small random numbers. And these are the weights or the parameters that we adjust over time with gradient descent. So learning for a neuron, or in deep learning, means finding useful values for these weights by nudging them a little bit iteratively with gradient descent. The way the neuron produces a value is we take a dot product of the inputs and the weights, or linear combinations. So we take each input value, we multiply it by its weight, and we sum that all up. And that's what's happening in the sum here on the left. And that gives us a single value between positive and negative infinity. let's ignore the activation for now. And we can use one neuron as a binary classifier. You can basically say if that value is greater than 0, then the image you're looking at is a cat. And if it's less than 0, then the image you're looking at is a dog. So a single neuron is a binary classifier. The activation function is a way to make this a little bit smarter. So let's say instead of doing linear regression, which is what we're looking at here, we wanted to do logistic regression. So we want to predict a number between 0 and 1, so we can interpret that as a probability. If you had an activation function like sigmoid, which is a squashing function, there's no machine learning there. A sigmoid just takes some value as input and squashes it to be between 0 and 1. Now we can say if it's greater than 0.5, it's a cat, and if it's less than 0.5, it's a dog. Anyway, that's what a neuron is doing. And now let's build up from neurons into a neural network. Here's exactly the same neuron drawn in a different way. So on the left, we're looking at an image, and let's pretend this image for some reason only has 4 pixels. And neurons are dense layers, which is what we're looking at here. They're very limited, and they can only take vectors as input. So they can't handle a square image. So usually what we do is we flatten the image into a vector. And that's what I've done here in this X. So if you look at X, X contains the pixels from the image. Flattening just means unrolling it into an array. Here we have these learnable weights, and these start life as small random values, and we adjust them over time with gradient descent. And to do the forward pass, we multiply each weight by the input, we sum it all up, and we add a bias, and that gives us a single output. And maybe here we're saying if that's greater than 0, it's a plane. If it's less than 0, it's not a plane. And here's a little cartoon diagram on a neural network that this might correspond to on the top. And really, I should have drawn it with 4 inputs because there's 4 inputs here. I just ran out of room. But anyway, it has 1 output. Let's take a look at this slide. So now we're going to build from our little neuron into something that looks a little bit more like a neural network. And if you look at the change here on the top right, we've added another output. So now we have 2 neurons. And if you look at the change in the math, what that means is we've added another row of weights. So now, instead of doing a dot product, we're doing a matrix multiply. We're doing W times X plus B, and we have a second bias. And now because we have 2 neurons, we get 2 output classes. So now our little, and this is the dense layer. The way you would write this in TensorFlow would be dense 2. It's a dense layer or fully connected layer with 2 outputs. And now we're doing multi-class classification. And what's really cool, we can also use our little network to classify 2 classes at the same time. This slide is a little buggy. Let's see. So we actually have 3 rows of weights now. And what that would mean is we have 3 outputs. So I should have a 3rd output here. And you can see that we're producing 3 outputs here as well. So pretend there's a 3rd neuron here. What I wanted to show you, though, was because we're doing a matrix multiply, we can classify 2 images at once. And here we're getting one prediction for each image in a single matrix multiply. It's still W times X plus B, but now we've changed X into a matrix. And you can see that the pixels from each image are here. The reason that I'm showing you this, and this is what I was joking about deep learning being sequential matrix multiplication that you'll see in a sec, is the non-joking thing is because we're doing lots of matmols under the hood, it means that GPUs are a great way to make this run much faster. So the reason that GPUs are so popular for deep learning is when we're classifying images with these networks and we're training them by adjusting the weights in this weight matrix, it's that is all under the hood matrix multiplies. And we can do that many times faster using accelerators like GPUs and TPUs. So that's why they're best friends forever with deep learning. So now I briefly wanted to show you what I mean by sequential matrix multiplication. And let's take a look at how this cartoon diagram might look with the schematics that I've been showing you earlier. And we briefly talked about this activation function called softmax. Really what this is doing is it's squashing the outputs of a dense layer into a probability distribution that ranges between 0. So with each output ranging between 0 and 1 and summing to 1. So you can interpret the output of the network as a probability. But what a single dense layer is, if you look at the bottom here, it's that W times X. It's that matrix multiply. And what a neural network is, it's the first dense layer, W times X, followed by a nonlinearity. And in this case, that's ReLU, which we'll look at in a sec, followed by another matrix multiply. So a neural network is a pair of matrix multiplies separated by a nonlinearity. And if you've taken a linear algebra class, great. If you haven't, great. The reason why we need this weird nonlinearity G, if you remember from from school maybe, if you're multiplying a series of matrices together, you can reduce that into a single matrix multiplication. And if you have the nonlinearity, it prevents that from happening. Without it, the second dense layer basically wouldn't be able to learn new features. And so we have to have these nonlinearities so each layer can learn different types of features so we can have this hierarchical representation learned. But anyway, let's see what we got here. So basically, let's take a look at what it means to apply a nonlinearity to the output of a dense layer. And there's many different types of nonlinearities. On the left here, we're looking at sigmoid, which is one we looked at earlier, and sigmoid basically squashes a number to be between 0 and 1. And on the right, there's a different type of nonlinearity called ReLU. You can see the math for ReLU below. It turns out to be simpler than sigmoid. ReLU basically functions as an on-off switch. It doesn't matter which nonlinearity, you have to use a nonlinearity to make to enable the network to learn different representations of each layer. As a piece of trivia, the nonlinearity that was very popular initially was sigmoid. And this is because sigmoid squashes a number to be between 0 and 1, so we can interpret it as a probability. And this makes a lot of intuitive sense. But if you take a machine learning class, you'll learn that sigmoid has some problems. And in blue, we see the value for sigmoid, and in orange, we see the gradient for sigmoid. And the basic idea is that when you have very large or very small values going into sigmoid, sigmoid saturates and becomes very flat, and the gradient becomes very flat and goes to 0. And this results in something called the vanishing gradient problem. It makes it very hard to train neural networks. ReLU doesn't suffer from that to the same extent. Basically, just to make it really concrete, what a nonlinearity is doing is it's taking the output of some dense layer and it's being applied piecewise just on the output. So here, for example, you can see the effect of applying ReLU to the output of a dense layer. Anyway, it's just transforming the output. And then that is fed into the output of the dense layer in the orange box here becomes the input to the next dense layer in the network. So that's what I mean by sequential matrix multiplication. And that's true even if you have this deep neural network. We add another nonlinearity and another matrix multiply here at the bottom. Again, it's one of the reasons that I love this field so much is if you had showed this to me, say in 2010, and said, like Josh, like I'm going to use this neural network. It's got all these matrices, and they all have small random values, and I'm going to train it with gradient descent to classify images. I would have said that this probably isn't going to work. It's not intuitive to me, and I think many people, that it's possible to train a network like this with gradient descent to get it to do what you want it to do, let alone that these neurons would start recognizing these beautiful patterns. And I think basically there's two reasons why our intuitions don't match this well. The first is that our minds are not built to reason about gradient descent in high dimensional spaces. They're just not. If you're like me, you can reason about things like decision trees, but not neural networks. The other reason why I think it's not intuitive to us that these would work is if you have taken a calculus class, you might have learned about things like global maximums and local minimums and stuff like that. And the first thing that I would suggest as to why this might not work is I'd say when you're training this thing, you're probably going to get stuck in a local minimum and it might not be very useful. And it turned out that in these super high dimensional spaces, especially with techniques like these smarter activation functions that don't saturate, although you're still going to get stuck in a local minimum, you can find one that's incredibly useful in practice. So you may not have the optimal neural network, but you have one that still does a phenomenal job of classifying things like cats and dogs. To wrap this up, I just wanted to point you to some educational resources, but a big tip, and the number one difference about testing machine learning systems and testing just regular software systems is that in machine learning, your code can compile and still be wrong. And what I mean by that is your network will take some input data and it will produce an output data, but that output, and it will produce an output prediction. That prediction might not be classifying the thing that you think it's classifying. And as an example of that, this is from a different talk, but here we're looking at a heat map of an image. And if you look at this image, it looks like it's a woman riding a horse. And we've asked the neural network using techniques like integrated gradients to explain why the neural network thinks that this is a horse. And it's highlighting the regions of the image that are important. And we can use this to debug what the model is actually doing. And here, if you look at the image, the surprising part is it's not highlighting the horse, but it's actually highlighting a chunk of the ground. And if you want to learn more about how this works, you can check out the TensorFlow YouTube channel, and we'll have a talk explaining this, I think, in about a month in detail. So if you're interested in learning more about this stuff, I have 3 book recommendations for you. And these are really excellent books. I own them all. They're some of my favorites. Basically, I just want to walk through very quickly what they are. Deep Learning with Python, and this is still being written. It's by Francois Chollet, who's the author of Keras. He does really great work, both in writing software, but also in explaining how it works. It's an excellent book on TensorFlow, and it will walk you through both the high-level APIs that I've showed you today, but also some of the nitty-gritty, lower-level details. And I think it's the best resource that exists today if you're new to TensorFlow and you'd like to get started. The book in the center, and I hope I don't mispronounce his name, learninng, who's done phenomenal work. If you're new to machine learning in general, this hands-on machine learning book is a lot longer, but it will start with classical ML. So it will walk you through things like k-nearest neighbors and decision trees and logistic regression, and then it will take you into neural networks. It's a phenomenally good resource. And the book on the right, it's the academic book. This one is freely available online. You don't need to buy it. It's called Deep Learning by E. Goodfellow and others. And if you're a PhD student, or you'd like supplementary material for the other 2 books that really dives into the math and the theory behind deep learning, it's a really excellent reference to have. And actually, the cover of it is an image from Deep Dream. So last thing, I'll stop talking. It's very important if you get any of these books, the 2 books on the left, that you get the 2nd edition. The first editions were written for TensorFlow 1. They're out of date. Get the 2nd editions, which are written for TensorFlow 2, which is much easier to use and what you should focus on. So thank you so much. It was really fun speaking with you. I wish I could see you all in person and just hang out and do longer events and take questions. But I hope this was helpful. Check out the books to learn more, and tensorflow.org/tutorials if you'd like to dive into to the code. So yeah, I hope to see you all in person in 2022. And that's all I've got for this talk.